local decoding, and we did it for Walsh-Hadamard. By just doing 2 queries, we can recover a bit of x. Then we did local decoding for Reed-Muller, which will also imply local decoding for Reed-Solomon. So here this was more complicated because it's a multivariate polynomial over a finite field. So to compute its value at a given point, we actually draw a random line through this point x, and then on the line we do Reed-Solomon decoding. Okay. Number of queries needed was size of the field. Now once we have local decoding for Walsh-Hadamard, Reed-Muller, we can also do it for concatenation by an idea that you have seen before. So we just wanted to analyze this carefully. So rho 1 is the local decoding parameter for E1, rho 2 for E2, and what the code E is doing is it first applies E1 to get sigma alphabet, and then every letter in the alphabet it will convert using E2 to binary. So there are m alphabets, x is sent to m alphabets. So you can think of the string y, the long string y, which is accessible through an oracle, you can think of it as E1x jth element, okay, jth coordinate of E1x on which E2 was applied. So based on the j's that E1's local decoder will require, okay, you go to those blocks, E1xj with E2 applied, you go to those jth blocks, and first you learn E1xj by E2's local decoder. So that is what we did last time. Step 2 is E2's local decoder with parameter rho 2. This was applied on the jth block, and this was applied again and again. So it was applied actually log sigma many times to recover E1xj, the whole symbol. Okay. So this will work if in this block the error is less than rho 1 fraction, and since E1 will require Q1 many j's, so you have to access those many blocks. So the error probability also should be made very small. So we actually repeat this process around log Q1 many times, and that will give us E1xj with a very good probability. Okay, so let's do that part. So step 4 will be about E1's local decoder now. So use E1's local decoder to query Q1 blocks. That is Q1 many j's. Okay, and in every j we had used E2's LD rho 2 as before in step 2 and step 3. So after applying E2's local decoder on those blocks, we are now moving to E1. So the answers are consistent with that of a string that is rho 1 close to E of x okay, which is, remember, E2 E1 x. So this is with probability greater than 1 minus 1 over 10 Q1 times Q1. Okay, for a single block the error is 1 over 10 Q1. For Q1 blocks, it can be at most 1/10. So the probability is 90% or more. So with this much probability, E1 will be able to, the answers will then be correct for how many of these blocks? So that we can write here. Since less than rho 1 of the blocks in Y can be at distance greater than rho 2. From the respective true block. Okay, remember that the overall cumulative error is rho 1, rho 2 or less. So which means that it's few blocks only which will be badly corrupted. Okay, by bad I mean more than rho 2 corrupted. So only less than rho 1 of the blocks are corrupted to an extent more than rho 2 in each such block. So in other words, if you look at the level of blocks, the error is only rho 1 or less. Okay, so whatever E2 has given in these Q1 blocks, out of them the error is only rho 1 or less. So hence when you will apply E1's local decoder LD rho 1, it will work fine and give you bit of x. So this means that E1's local decoder outputs xj with probability already it was 0.9 came from what E2 did, E2's local decoder did, and after that what E1 is doing, E1's local decoder is doing, there may be error of 1/3, that is by LD rho 1's property, local decoder's property, which is more than half. Okay. So with probability more than half, you will get xj, and number of queries is so we in the initial steps it required log q1 times log sigma, and there is also a q2, right. So it required q2 log sigma, and this was repeated log q1 times just for probability boosting, and for even sake number of blocks will be q1, so that's another q1. Okay, so this is the number of queries, and the success probability for xj is good. So this finishes the local decoder for concatenated codes once you have local decoding for the individual components E1 and E2. Okay, this was actually quite straightforward, but when you look at the parameters, they look complicated. And what this means for us, so for Walsh, Hadamard, Reed, Muller local decoder, the number of queries is So, number of queries will be sigma is the size of the field, and which is also equal to the queries you make for Reed-Muller, right. So, which is Q1. So, you get Q1 times log Q1 whole square. Q2 is for Walsh-Hadamard, which was only 2. So, that is just constant. So, you get Q log square Q, okay, which is basically linear in Q, just slightly more than linear in Q. That many queries, handling up to how many errors? What is the row parameter? So, that is row 1 times row 2, right. So, for Reed-Muller you will get 1 by 6 d plus 5 by q minus 1, and for Walsh-Hadamard it is 1/4 errors, which is around 4% errors. Where Q is the size of the field. And also note that the message length is it is around what is the stretch of Reed-Muller, right. So, that is d degree L variate polynomial. So, you get d plus L choose L, and code length is Reed-Muller sees x as a polynomial L variate d degree. So, that is d plus L choose L, many coefficients or many values that defines a polynomial, multivariate polynomial, and then Reed-Muller will evaluate it on every point in the field. So, that is q to the L, that is the code length. So, now observe in terms of the code length. In terms of code length q to the L, that is the length of y, it is very long, and this algorithm local decoder is making only q queries, okay, which is much less than q to the L, and it will give your favorite value amongst these d plus L choose L values with good probability, and even errors can be quite a lot. 4% of y may be corrupted, and errors around 5%. Okay, so this is a very important, interesting algorithm, but this won't be enough. Remember, our final goal is hardness amplification from worst case to average case. So, for that 5% error is not enough. We actually should be able to handle much more, closer to 50% actually, something like 49% errors we should be able to handle. So, that is what we have to do now. So, our final goal is to show if f is a worst case hard function and E is a locally decodable code, then on the truth table of f, okay, look at that long string 2 raised to n on n bit input. The values that f takes on all possible n bit inputs is 2 raised to n values. So, that is called the truth table of f. On the truth table you apply the locally decodable code E, okay, and you will get a slightly bigger string, and that defines a function f prime. truth table G of G is should gives a average case hard function. Okay, that is what we want to show. So, average case hard means that it should be half minus smaller than half many inputs. So, hard on close to half minus delta errors, half minus delta inputs. Right. So, this actually if you think about this carefully, this will require a local decoder for E which can handle errors close to 50%, okay, which is asking for too much. So, implies that we need an E that is locally decodable up to half minus delta errors. So, this type of decodability cannot be unique. Meaning that there will be many X's for a Y so corrupted, the X's options for messages will be many. Okay, it will not just be one, but there will be super constant many X's. Now, the question is how many, and the next question is whether you can computationally list them. So, we relax decodability, unique decodability to that of finding a list. Okay, so this is called local list decoding. But whether it is possible or not, that will depend on how long the list is. So, let us first show that, and that is called Johnson's bound. So, if you have a map, that is a code, is an error correcting code with distance at least half minus epsilon, then for X's and delta slightly bigger than epsilon, there exists at most 1 over 2 delta square many code words y1 to yl such that they are close to x. Okay, so the number of y's that are close to x, that is what we are interested in. How many y's are close to x? So think of x as a corrupted code word, and the question is how many code words are close to x. That number is, in terms of delta, it is inverse polynomial. So it is 1 over 2 delta square. In terms of epsilon, you can think of this as 1 over epsilon. Okay, so for distance half minus epsilon, the list is 1 over epsilon, and that's a very good bound. So for all I1 to L. Okay, so you can think of this as the following picture. So you look at the ball around x. Okay, half minus delta. Look at this radius ball around x, which means collect all these strings which are fractional Hamming distance less than half, exactly half minus delta or less. And in this ball, how many code words can you trap? So say y1 is a code word here, y2 is a code word here. Now remember that code words themselves are far apart in the space, right, because of the distance of E. So the distance between them is already half minus epsilon. So since y1 and y2 are far apart, the intuition says that you cannot pack many yi's inside this ball. Okay, because this half minus epsilon is more than half minus delta. It's more than the radius, so you cannot pack too many of them. But how many? What is the bound? How do we upper bound this? That's the thing. So let's look at the proof. So intuitively, we cannot pack many yi's inside the ball. And we will analyze this in terms of distances and inner products. So we analyze using inner product. So let us define inner product so that it captures this Hamming distance well. So define the string z1 to zl plus minus 1 coordinates. Remember the code word is of length m. Okay, so let us define the string zi's such that what is the kth location of zi? This is one if we will be associating zi with yi, right? So one if yik is equal to xk. Okay, so if the kth bit of yi and x is the same, that's indicated by zik, otherwise negative. And now, since distance of x and yi is small, smaller than half minus delta. So, what you get is, go over all the k's, all the locations of x and yi. So, that will be, see, distance being small means that x and yi overlap in many locations, they are similar. So, which means that zik will be a lot more positive than negative. So, how many times positive? Half plus delta m times positive, otherwise negative, which is half minus delta m. Okay, so that is 2 delta m. That's one equation. On the other hand, the opposite pressure is that yi and yj have to be far apart by the notion of distance of E. So, that gives you something else. So, since yi, yj are away, what you will get is the inner product of zi, zj. Now, since yi, yj are they differ a lot, so they overlap in fewer places. So, which means the inner product is expected to be small, right? How small? Let's go over the coordinates. And now zik, zjk, they are of the same sign if they match xk, else they are opposite. So, in how many places will they match xk? Well, that will be fewer than half plus epsilon by the above inequality. And the negatives will be more than half minus epsilon. Right, which is 2 epsilon m. So, let us number these two conditions that we have. This is condition 1 and this is condition 2. The first condition is kind of saying that zi is a long vector. Second condition is saying that zi, zj are, the inner product is small, which means they are almost orthogonal. Okay, so these are long vectors and they are almost orthogonal. These are the two conditions geometrically that we have written. And how do we combine them to get something useful? So, let us define W sum of all the zi's, that vector. Okay, so how long is W? Length of W. It will involve both zi inner product with itself and zi inner product with other zj's. Now Zi with itself will coordinate by coordinate, if you see, that will be all +1 values, right. So that's M. And Zi Zj inner product for different ij, that will come out to be 2 epsilon m. Right, which is less than equal to, so you get ml lm plus epsilon is smaller than, what did we take, delta square. So epsilon is smaller than delta square, so you get 2 delta square, and number of ij pairs is definitely less than L square. So you get this. Okay, that's your equation 3. Also by equation 1, you can get more information about W inner product itself, right, because equation 1 is saying that this Zik is, they are kind of large. So that should mean that W with itself inner product should also be large. So let's think of it that way. So you will get sigma Wk, which is all k and all L i's. So Zki, Ik, sum over all the Zik's, that will be by equation 1 at least, what was it, 2 delta m times L. Okay, you can think of it as equation 4. And now equation 3 and 4 are somehow opposites. Okay, so we'll combine them and get the answer. So by Cauchy-Schwarz, you can see that essentially average of squares is at least square of the average. Okay, that inequality. So which means that inner product of W with itself, right, is at least sigma Wk, which is by equation 4 2 delta ml square by m, which is 4 delta square L square m. Okay, so inner product of W with itself is large, this is what you have deduced, and previously you deduced that it is small. So that will give you the result. So combining with equation 3 gives you that 4 delta square L square m is less than inner product W with itself which is less than equal to Lm plus 2 delta square L square m, which implies after some simplification you will get 2 delta square L less than equal to 1. Delta is taken to be positive as well. So, because of the non-zero delta you can divide. Okay, and since delta was more than square root epsilon, you will get 1 over 2 epsilon also. So, basically for error correcting codes of distance half minus epsilon, the list is no longer than 1 over 2 epsilon. Okay, that's a beautiful result. List is small basically. So, next question would be whether you can find this small list, and the error is very close to half. Okay, so the list is small. The next question is whether this list can be efficiently found and locally found. So, can we compute the list efficiently and locally? Right, locally means that by minimizing the queries to the corrupted code word. So, we will actually do both. So, let us first list decode read Solomon, that is a fundamental decoder. Okay, this is a famous theorem by Madhu Sudan'. So, he showed that there exists a randomized polytime algorithm that given a corrupted read Solomon code word, which means that you are given evaluations, some of them are wrong. Evaluations of a polynomial. So, that given AI BI pairs over a finite field, let us say m many pairs, returns the list of all degree D. Suppose the polynomial whose evaluations you are given, corrupted evaluations, is of degree D or less, and BI's let us say close to half of them are corrupt. Okay, so, there will be many polynomials actually which are consistent with this data. So, the algorithm will output all of them, returns the list of all degree D polynomials G such that the number of i's on which G matches. Okay, this is at least square root of dm, square root of 2 dm. Okay, this can be significantly smaller than m. So that is for distance greater than 1 minus d minus 1 by m, right. This is the distance of Reed-Solomon code. The list decoder handles one minus for length m over the field alphabet for length m. The correct values are 2d by m whole square root, and the rest is all erroneous, right. So these many errors are being handled. Okay, so this is also what you saw in Johnson's bound, that I mean in the sense that there you had a half, here it's 1, but this d over m versus square root of d over m, right. This seems similar to Johnson bound, but remember that this is not a binary code, so it's non-binary alphabet. Okay, so in Johnson bound you had we are talking about half minus delta and half minus epsilon. This is the non-binary version of that, you can say, but it's very good. Okay, this is able to handle a lot of errors. It can be easily seen to be, I mean it seems that the errors can be close to 100%, still it is able to give you the list. It's so good. So how do you do this? What is the idea? The idea, just like Reed-Solomon decoder, is to introduce an auxiliary polynomial. So use a bivariate auxiliary polynomial qxy to fit the data. Okay, and then once you have this q, the auxiliary polynomial, you factorize it, and the factors will magically give you the list. So compute a non-zero q bivariate over the finite field f such that q ai bi is 0 for all the input data points, where the weighted degree of q is this bound 2dm square root. Let's call it t. What is weighted degree? So this is the max of I plus dj for all monomials in Q. X to the I, y to the j in the support of Q Okay, so weighted degree is just like degree, but now x and y have been given different weights. X has been given weight 1, y has been given weight d, because you should think of y as being this unknown message polynomial, okay, which had degree d. So y is given degree d, and then any monomial xi yj has degree I plus dj, and you maximize over that. So number of monomials that Q can have. This is how much. So you want I plus dj maximum to be t, right, which means that I can be at most or j can be at most t by d. So j goes up to t by d and starts from 0, and for a fixed j, how many i's? So the i's will be t minus dj many. So this is the number. I is at most t minus dj, right. So you get 1 plus that. I can also be 0. So go over all these j's. That's the number of monomials that Q can have for this weighted degree t, which is what? Which is simple calculation. So it's 1 plus t times this for the 1 plus t contribution, and for dj contribution you will get minus t by 2 times t by d right, sigma j. So that is t by d times t by d plus 1 by 2, and d multiplier is there, which is at least how much? So we can take out 1 plus t by d, and what remains is 1 plus t minus t by 2, around t by 2. In fact, this is equal, not greater than equal to, it's exactly equal. Yeah, now you can approximate this. So this is at least t by d times 1 plus t by 2. So that's t by d plus t square by 2d, and you can see that t square by 2d is m, right, from here. So you get more than m. So number of monomials is sorry, let's make it like this, equal. So number of monomials in Q, this unknown Q, so coefficients are the unknowns, and the number of unknown coefficients comes out to be more than m, right? And from the data, which was m pairs, you will get m constraints. So, the constraints are fewer than the unknowns. So, number of unknowns is greater than number of equations in this homogeneous linear system. Okay, so that means step 1 will find a Q. This is the step and also the analysis. So, it can actually be computed, and since it is as simple as solving a linear system, you can do this in polynomial time. It will always exist. One option at least will exist. So, you have a Q that is fitting the data, and its 1 comma d weighted degree is at most t. Once you have this Q, what you do is factorize factor Q. So, that's step 2. So, factor Q using an efficient bivariate factoring algo over finite field F. Okay, so these exist, you can look them up in the literature. So, you will get irreducible factors of Q, and the final step is for factors of the form y minus px, degree of p less than equal to d, and number of i's on which it fits ai bi greater than t, output px. Okay, so this is the full algorithm. Fit the data with degree bounded Q, factorize Q, and output the factors that are linear in Y, and which satisfy this degree condition of the message polynomial that you were looking for. Degree should be less than equal to d, and it should fit the points on more than t locations. Okay, so why will it work? So, the reason is any gx that fits greater than t points it will satisfy the following property. It will actually be, when you substitute in Q x comma gx, right, that will be 0 on greater than t distinct AIs. That is one thing. Q will vanish at gx because simply because when you look at AI comma GAI, GAI is equal to BI on more than t many AIs, right. So, and Q fits that. So, Q is vanishing. not completely, but on t many or more than t many values of AIs. And second thing is that if you look at the degree of Qx comma Gx, this is less than equal to t. Right, this follows from the weighted degree of Q. Which we have set to be less than equal to t. So, Q at x comma Gx is a degree t polynomial which is vanishing on more than t values, which could only mean that it is 0. Which means that y minus Gx divides Qxy. Okay, so any degree dgx that fits a lot of points actually appears as a fact, making hence factorizing Q made sense in step 2 and our output is correct. Okay, so this algorithm with the ideas and the descriptions given, analysis given, finishes Sudan's theorem. Okay, so for t square root of 2 dm, more than these many matches, if G matches more than these many places the data, then you will find G and the list will be small. So, list will be small because this whole this algorithm is a polynomial time algorithm. So, automatically the list is small. So, that finishes the proof. And we actually also get this corollary for the length of the list. So, Reed-Solomon of distance 1 minus d minus 1 by m, right, for d degree polynomials has a list decoder handling one minus 2d by m square root errors and the list size is that you can deduce by looking at the degree of Q with respect to y, and it comes out to be handling these many errors and outputs list size at most 2m by d. So, this will follow from degree of Q is t, right. Degree of Q is weighted degrees at most t and you divide it by d. So, that gives you the degree in y. That is the simple proof. So, proof is that degree of Q with respect to y is at most t by d, which comes out to be 2m by d. And since you output the factors y minus px, Px cannot exceed more than square root of Tm by d. Okay, so that is the complete description of Reed-Solomon list decoding. Now we move to the final concept, which is local list decoding. And the goal here will be to find the list by making as few queries as possible to a long corrupted code word. The focus will also be on the queries made. So remember that this Reed-Solomon that we did is not was not local, because we actually fitted the whole data to find Q, right? So we were actually querying everything. This is what we want to improve upon. So let E be a binary code. And let epsilon be half minus rho for rho between 0 and half. Okay, rho will be the again this local list decoding parameter. That many errors. There is no meaning to epsilon except how close is rho to half. Okay, at half for binary code you will not be able to do anything. But just below half, what can you achieve? So an algorithm D is a local list decoder for E handling row errors if so we want to say that, let's do in a different color. If for every message X, for every corrupted string Y, that is close to EX, there will exist, let's say, an index for X. So there will be there in this kind of error, a very high error row close to half, there will be many X's. So once you are given the index of X that you want, so that we'll call I0. There exists an advice I0, which is a number between 1 and polynomial in n by epsilon. Such that such that for all locations when you are given input this index or advice, that is which x do you want, implicitly this is what you are capturing, the jth bit of x, that location, and an oracle for y. D will run in time polynomial in, again very few queries, right. So, log m for m length corrupted code word, log m time, and also depends on n over epsilon. If you are very close to half, epsilon is 0, then this is not possible, but just below half it is possible, this much time. So, D runs in this much time and outputs xj with probability 2/3. Okay, so that is the definition of a local list decoder, handling row errors. For any message x and corrupted code word y given as an oracle, once somebody gives you an advice, then any jth location of x can be found with high probability and efficiently, very efficiently. So, you could think of I0 as the location of list, location of x in the list. Which is of course unknown. And you can ask for the whole x in place of xj. Okay, so you, because if you can output xj with high probability, then by repetition you can also output all, because the same I0 will work for all the j's, right. So, it is as good as you can also output the full string x. So, that is the concept, and we will now do the final steps in this course will be to do local list decoding for Walsh-Hadamard and Reed-Muller. That will finish the course.